I have the pleasure of introducing Dr. Tariq. I work in medical imaging, and from time to time, someone would say, maybe if we're doing deep learning, we should combine some health records or some pathology results with the images and see if we can't get better results. And inevitably, we'd all say, yeah, that's a good idea. Let's put it on the to-do list. But no one ever did it. Well, while we were talking about it, Dr. Tariq was succeeding at doing it. She comes to us from University of Lahore in Pakistan, where she received a bachelor's and a master's. She then received a master's and a doctorate from the University of Central Florida. She completed a postdoc at Emory University. She's been a postdoc at the Mayo Clinic, and she's going to talk to us about some of the successes she had combining disparate sets of information with machine learning. Thank you for joining us, Dr. Tariq.
Thank you, Nick, for introducing me.
So what you said?
I don't think any response to the letter, but I think it was great.
Yeah, you did. I think you yeah. So.
Sorry, Dr. Tariq, I think somebody had the mic open.
Oh, okay. I thought like it was some question for me right at the beginning of my talk.
Go ahead, please.
Hello, everyone. I'm here to talk about my research on multimodal data analysis for biomedical applications. So we all know we are living in the age of big data. Tremendous amounts of multimodal data is being generated every second of every day. And we're talking about visual data, textual data, geolocation data. But when we talk about healthcare system in the context of medicine, medical systems, we are talking about imaging studies like CT, chest X-ray, MR, ultrasound. We also include clinical notes and radiology reports, which is obviously textual data, and then lots and lots of tabular data recorded in electronic health record systems. What we need is data-driven intelligent decision-making systems. And my research interest, it lies in developing multimodal data analysis systems that can enable this kind of intelligent decision-making. Intelligent decision-making systems, in my opinion, they need to have these two desirable characteristics. One of them, they need to be generalizable. So similar framework, it should be replicable to solve like similar problems. And they should also be transferable between similar domains. Another thing, they need to be explainable as well. So we have a variety of approaches based on gradient-based approaches or ablation studies. But as I'll show you, that a lot of innovation is still required to be able to explain more complex models that are being built these days. A little bit about my background. I joined University of Central Florida in 2011 as a Fulbright scholar and a PhD student. There I was working on problems like image captioning and semantic network of named entities. So that's where I gathered all my expertise in computer vision, NLP, image processing, machine learning, and deep learning. And then into 2017, I moved back to my home country, Pakistan, and I taught there for 3 years in a computer science department. And I was focused on AI and machine learning courses at both graduate and undergraduate levels. Then in 2020, I moved back to US and I joined Emory University, Georgia as a postdoc fellow. And then from there, I moved on to Mayo Clinic, Arizona. And both of these locations, more recently, I've been using same computer vision, NLP, machine learning, deep learning techniques to build these fusion models to solve some biomedical tasks. I'm first going to introduce some work from my doctoral thesis. So at that point, I was interested in image captioning, particularly news image captioning. So what's so different about news images? Here's a sample of news images along with their captions, and here is a sample of images from MS COCO dataset, which is a very popular image captioning benchmark. So you can see captions with news images, they're much more semantically complex. You need to understand the context of the image before producing or generating any of these captions. On the other hand, MS COCO captions, they are mainly just a description of the objects in the image or maybe some basic level of activity annotation. Good thing is that with images, with news images, you have a lot of auxiliary information sources like news article itself and the metadata associated with the news article that you can use to understand the context. Challenge is that it becomes a multimodality problem. There is the visual data, free-flowing text of news articles, and metadata as well. The way text as discrete context categories, and then figure out estimation, then figure out association of any image with all of these context categories. And then the task is to make sure that your captioning model is conditioned on this context information. This work was published in IEEE Transactions on Image Processing. To experiment, I collected my own data set of about 20,000 news articles, along with their images and their captions and all of their metadata. Since it's a multimodal problem, I use techniques from both computer vision and NLP. For example, when it was time to deal with images, I decided to use scene analysis. So Places 365 was this huge data set where each image was tagged with 35 scene labels. So I used a deep learning based model, CNN trained on this Places 365 data set, and I generated feature vectors from my images. These feature vectors I then used to create clusters or scene clusters through an adaptive hierarchical clustering process. So one cluster, it would contain, images with similar scenes, and you can say there is a sample of one cluster, and you can see like if images they have similar scenes or similar backgrounds, there's a chance that their captions they have some similar context as well. The task is to figure when you get a new unseen image, how do you figure out its association with these scene clusters? For this, I used Gaussian kernel over minimum distance. So basically the distance between scene features of the new image and its closest match from any scene cluster. Moving on to the NLP part, we had this long free-flowing text in news articles. There I decided to use topic modeling. Topic modeling is a generative process which assumes that every document is a collection or distribution over topics, and every topic is a distribution over words. So this is an unsupervised modeling process where I decided to treat every topic as one discrete context category. And this inference process, it also gives me association between every article and all of the topics. And we can just assume that accompanying images, they have the same distribution over topics. Dealing with metadata was rather straightforward. For example, I had these news section labels. So if the image belongs to that news section, for example, word, politics, or media, or education, then the association between that context category and the image is 1, otherwise it's 0. So after I had these context categories collected from all of these multimodal sources, and their association with all of the unseen images have been estimated, the next task was to figure out actual annotations for the image. So for this, I used this generative process, which estimates the joint probability of words and images. And I made sure that this process is conditioned over the context information that we've just estimated. So if I just look at the top few words from this distribution, I get annotations like tokens, token annotations for all of the images. Final goal is to have sentence-like captions. So for that, I decided to use an extractive approach, because with these images, there is a large amount of grammatically correct and relevant text available in the news article itself. So the task is to extract the best sentence from the article that can describe the image and that can be used as a caption. For that, there are 2 sources, the image and the article itself, to figure out that suitable word distribution for the caption.
Out way too fast, like in bed, before the team could get there with the equipment. Placental, and that happened in 2014.
Sorry again, we have an open mic. Sorry.
Okay. Okay. Anyway, so coming back to the image and the article. With images, As I mentioned earlier, we had this process of estimating the joint probability of words and images. So I decided to use the same distribution. With the article, I again estimated this this distribution. I'm assuming that this was again in a mic. Michelle, can you please let me know through chat if there is an actual question? Is that okay? Because I'm not sure if there's a
No,
question.
Dr. Tariq, so sorry. It seems that we are unfortunately experiencing a lot of unintendedly open mics. So sorry. Go ahead.
Okay, no, that's okay. I'll just wait for something to pop up in the chat before I think that it's a question. Okay, anyway, thank you very much. So with article, I decided to estimate this distribution, which is basically ignoring the image, and it's just trying to decide whether a word should be part of the caption if it is part of the article. With these two distributions, I did weighted aggregation, and then I did an extractive process, basically going through all of these sentences of the article and finding the one which best matches the distribution that I've estimated. So when it's time to evaluate this kind of model, people usually evaluate captioning models the same way they evaluate machine translation models. Because in both cases, you have a predicted sequence of words and you have a ground truth sequence of words, and you want to see how closely they match. For example, this TER, the translation edit rate, it's simply it's an average number of edits required to convert one of your predicted sequences into your ground truth sequences. Meteor is a little more intelligent. It can take into account synonyms, but of course, then it becomes language dependent. Through both of these models, both of these evaluation measures, we realized that the context-based extractive approaches, they tend to outperform several baselines. There is a sample of the extracted captions and the ground truth captions. In some cases, the actual ground truth caption is very brief, while the extracted caption, it gives you a much more background, much more context about the image and the article itself. Another project that I wanted to quickly touch upon was this semantic understanding of free-flowing text of news articles. So these news articles, they mention names of people, places, organizations, the tokens that we call named entities. And there have been studies to show that named entities, they are the most important content out of any free text body. Most of the queries, they are about these named entities. So it's good for query answering engines to first recognize these entities. For those, we have like named entity recognizers, and then understand the relationships between them. Usually understanding the relationship between entities, it will be done through an ontology where you have like a structured model, and there is a predefined types of relationship supervised approach where basically you learn a predictor for your named entity. And then the connection between two named entities, it's decided based on the similarity in their predictors. And if you're using a more interpretable predictor, like maybe a group lasso model, you can even assign a type to that relationship. Data was required, was completely self-supervised, and this work was published in IEEE Transaction on Pattern Analysis and Machine Intelligence. Now I'm going to use some of my more recent research that's about all fusion modeling for biomedical applications. Here, the overall vision is about digital phenotyping of patients. You get a lot of data regarding these patients. You have their clinical notes, you have their imaging studies, you have their tabular data, electronic health records. So the idea is to build these fusion models, which can combine these different data modalities together, and then build patient representation vectors. And I want to keep this process as much self-supervised as possible, because we all know getting labeled or annotated or tagged clinical data is an expensive process. Once you have these patient representation vectors set up, you can target a variety of downstream prediction tasks, from clinical event prediction to treatment planning to survival analysis. Two main streams of projects that I want to introduce in this area. One is regarding language modeling, and the other is fusion modeling for clinical event prediction. Language modeling, simply put, you're trying to figure out a semantic representation, a semantic feature vector for your textual data. That can be a word, sentence, paragraph, maybe a whole radiology report or maybe a sequence of your clinical notes. You want to figure out what their semantic feature vector, semantic representation would be. Challenge, one good thing is that when you have this textual data and you can do this language modeling, you can figure out their semantic feature vectors. You can maybe put it through a predictive model and come up with some labels. For example, maybe you have radiology reports and you want to assign malignant versus benign labels. Good thing is that these, if we are talking about radiology reports, they are also associated with some imaging studies. And it's hard to get those imaging studies annotated. But if we have labels coming from their radiology reports, they can act as pseudo annotations or pseudo labels for these imaging models as well, for imaging data as well. And this can help you train your complex imaging models. Challenge often in this domain is that you're dealing some semantic domain shift. For example, even if you're talking about radiology reports for the same type of imaging study, they may be written under two different templates. Report may be written as free-flowing text. Report may be written as by following a very strict template. So there's often, if you plot them or if you visualize them in a semantic space, you would see that your reports, they seem to occupy different areas of the space. So challenge becomes the generalization. If you train any model in one of these semantic spaces, how do you make sure that that generalizes to that other part of semantic space as well? So this becomes an important problem. Solutions, they often are, some text standardization where you can, reduce the semantic distance between these different types of reports, domain mapped language modeling, or even transfer learning. And I'll introduce some of these techniques in my work. One of the projects in this stream was this about prediction of standardized score for coronary CT exams. So coronary CT exams, they're done to assess the blockage of coronary arteries. In 2016, a standardized score called RADS was proposed. So RADS assigns a score between 0 and 5. The higher the score, the worse is the blockage in your coronary arteries. Again, in our overall vision, we wanted to do this patient phenotyping for coronary artery disease patients. For this typing, we have these imaging studies, coronary CT exams. We also have their clinical data. So we want to train a model, one model, maybe one branch of the model for clinical data, one branch of the model for imaging data, and then combine it so that we have this comprehensive patient phenotypic embedding. To train this branch of this whole network, you can see that you would need some sort of annotated imaging data. Ideally, someone would sit down and mark where the artery is or where the blockage is, but this can be a very expensive process. Instead, what we propose is that these coronary CT exams, they are tagged with reports, and we can use these reports to generate labels. RADS is a nice example in that. RADS score, for example, RADS score of 4, it means 70 to 99% blockage. So it doesn't give you the exact amount of blockage. It doesn't tell you where that blockage is, but at least it gives you some label for the accompanying imaging study. So challenge is that first, the standard was proposed back in 2016. So you have a lot of reports before 2016, which are without RADS scores. Even after 2016, and we were collecting data from Emory University Network, which is a large network, and we could still find only a few hundred reports in the past 5 years, which were written under RADS templates and which had RADS scores assigned to them. So ideally, we should be able to train a model which can predict this RADS score using the text of the report. But again, the problem is the generalization. Because in this space, we actually plotted this in two-dimensional space. So this is semantic two-dimensional representation of the semantic space. On this side, you see these structured reports, and we have fewer structured reports. These, we are calling it structured because they were written under the template provided with the RADS standard. And on the other side, you have a large number of untemplated reports, unstructured reports. If we want to train a model that can predict RADS, we can do it over only on the structured reports because we have labeled data available for them. So we have a model over here that we can train. How do we make sure that it generalizes to this domain as well, to this space of the semantic, this portion of the semantic space as well? And here are two samples. You can see this top one is a structured report. It's written under that template structure. You have sections, you have subsections, and then you have this kind of free-flowing text type report as well. So there's an actual shift between different types of reports. The solution here, one thing that we tried was this dictionary-based text standardization. So Clever is a popular clinical dictionary that takes clinical terms, and if they are synonymous, they are mapped to the same code. That's how it reduces the variation in the text. But this is a generic dictionary. It has nothing to do with coronary anatomy or cardiovascular domain. So we augmented this dictionary to include all of the coronary anatomy terms, as well as all of the terms indicating blockage, like plaque or stenosis. Another idea is that if you're doing like generic language modeling, maybe you can afford to ignore mathematical symbols or digits. But in this particular case, actual blockage is reported as like a range, like 70 to 99%. So we make sure that our text standardization, it preserves these mathematical symbols and ranges and digits as well. So with this kind of text standardization, we are basically trying to bring these two types of reports closer to each other. Still, we have labeled or like CAD-RADS score available for only the structured reports. Even when they are close to each other, we can only train a predictive model on the structured reports. So what we do is we actually train an unsupervised language model, a skipgram-based word-to-word model. So this model trained over this domain mapped language space. So this gets basically semantic information from both templated and untemplated reports. Then we use this predictive pipeline. Basically, we tried LSTM and 1V CNN, and this is a predictive pipeline, so you need table training data, but we make sure that this predictive pipeline is initialized by the weights of our domain mapped language model. So that way, even though this model is this pipeline is trained or fine-tuned on just the structured data, we do get some information from unstructured data as well. So with this kind of structure, we were able to get close to 98% accuracy on the structured reports. But the interesting results, they are on the unstructured reports. The problem also was this huge class imbalance. Lower scores of 0 and 1, they are much more common than higher scores of 4 and 5. So here is the class-wise performance. And we report both accuracy and one margin accuracy. One margin accuracy simply is like if there is a difference of 1 between the predicted and the ground truth score, we'll consider it accurate. Why do we do this? Because there have been studies on inter-rater reliability of these scores. So two human annotators, they might differ by their scores, assigned scores, they might differ by 1. And these two categories, CAD-RADS 2 and 3, they are the two most confusing categories for human annotators. And this is the same for our model as well. So as you can see in this confusion matrix, our model is most confused in these two categories as well. So this domain map language model initialized predictor pipeline, it performs the best, and even its mistakes, they're understandable, or they're more aligned with like how humans would do that. Another project in this domain was about these liver cancer reports. So we had these liver scans, and the domain shift that we dealt with this in project was coming through imaging modality. So we had these ultrasound reports and we had these MR reports. They were both scanning the liver. So of course there were common terminology, but there was also quite a lot of distinct terminology based on the imaging modality. And the task was to be able to predict malignant versus benign label by just looking at the text of the report. These two modalities, as you can see, ultrasound is it's like a cheaper modality, more like a screening exam. So you get a lot of exams and you get a lot of reports. MR, on the other hand, is a more expensive modality, so you get few training examples from there. So we wanted to make sure, like, if we are training a model for MR reports classification, we are taking advantage of this related but distinct domain of ultrasound. So the solution we decided to use was this transfer learning. So we decided training a language model on our common domain, that is ultrasound. Then we take it to the MR domain. So in this way, we add the MR specific words in this language model and we fine tune them. And then we try to classify the MR reports. We did the reverse process as well. Started with MR, fine tuned over ultrasound, and then tried classifying the ultrasound reports. Here is again a semantic representation. You can see these closely clustered yellow dots. These are the original ultrasound words. Then these aqua blue dots, this is the updated fine-tuned MR language words. These are the new words added by the MR domain. And as you can see, these, it's a zoomed in version. So you see these new words, which are synonymous, they're mapped closer to each other. And it's a sign of quality of your language model. In this case, as you can see, one domain is much more common than the other one. So here, what we are trying to do is that we train a language model on our common domain, and then we take it to our rare domain and we fine tune it further. And then we used a predictive pipeline to do the actual classification. So in addition to the MR versus ultrasound shift, we also had templated and untemplated reports in these areas as well. So untemplated reports are again those free-flowing text type reports, which are harder to classify. So if you look at the results, you can see that in the templated reports, even by using just a language model trained on MR, you get very high performance. So there's little room to improve. But if you look at the untemplated report, you get only 26% F score for the malignant class, which is obviously the class of interest. But if we use our fine-tuning approach, we get close to 65% F score for our malignant report. Here is again a symmetric representation. So this is the original MR language domain, and you can see the malignant and benign reports. They're pretty much overlapping in this space. So it's hard to classify one from the other. On the other hand, in this space, which is the fine-tuned space, you can see that they are much more separated. So that results in better classification performance. In terms of explainability, both of these models, since we're using only CNN and STM, they are explainable through gradient-based approaches. So we use this layer-wise relevance propagation, which assigns an important score to the tokens of the report given a particular label. You can see this is from the RADS project, and as you can see, this is a report with RADS score of 4, and the model launched to put the most emphasis on 70 to 99%. That's the actual range for RADS score of 4. This is from the MR classification project, and you can see model launched to look at the kind of important terms like fat or iron deposition and liver lobe. So we understand that the model is looking at the right terminology. Because we're using this dictionary-based standardization, text standardization, so you can see this long term like left anterior descending artery. Model knows that it was mapped to the same token, same code. So model knows that it's one term and looks at it as a whole rather than looking at it in parts. So overall, these projects, they are of course transferable. We are talking about transfer learning from like similar domains or domain map language modeling. They're also explainable through gradient-based approaches. In my overall vision of research, it fits into that self-supervised modeling. One, because language models, they are self-supervised models to begin with, and they are also fulfill that idea that you can maybe use these labels to further annotate your imaging studies and build this kind of self-supervision into your imaging models as well. Another line of project that I want to introduce is this fusion modeling for clinical event prediction. Clinical events, they can be admission into hospital, discharge, ICU admission, or maybe mortality. So more like a prognosis approach. You have a patient, you want to see how the disease would progress or how the patient should be like low risk or high risk, or what are the chances of an adverse event happening, like mortality or maybe ICU admission. If we can do this kind of prognosis on a larger scale, it may even help with the resource management at the hospital level. If you know how many patients would be needing ICU admission, let's say in the next 24 hours. Challenge again is the multimodality of your clinical data. So you have this clinical data, codes, CPT, ICD-9. You have these lab results, medications, demographics. Sorry. And you also have these imaging studies and clinical notes. So overall, we need some sort of fusion modeling to be able to fuse all of these different data modalities so that we can make one comprehensive prediction. First project in this line is about this EMR-based prediction for COVID-19 patients. The idea in this case was that patient gets tested for COVID-19. So if the patient is positive, can we tell that whether the patient would need hospitalization or patient can just go safely quarantine at home? And for that, we decided to look at 1 year worth of clinical history, electronic health records for the past 1 year of those patients. And this work was published in NPJ Digital Medicine. Problem here was that because of this unique scenario of COVID-19 pandemic, you get these patients who have, like in the past year, they've had regular contact with the same healthcare facility. So you get a lot of information about their clinical history in the past year. On the other hand, you get some of these patients who have little to no contact with that healthcare facility. So their data is much more sparse. If you're going to do any kind of temporal modeling, you need to figure out some time intervals, like what's your one time interval. You can do quarterly or monthly time intervals, but in any way we tried, we realized that we end up with lots and lots of intervals for lots and lots of patients, which are just empty because we don't have any information about them for that particular interval. The solution was kind of simple. We went with this uneven interval. So we decided to use the past 15 days as the current interval and everything beyond that as history. So with this kind of, and we decided to put equal emphasis on both of these intervals. So this way, if you have patients who have like no contact or little to no contact with the same healthcare facility in the past year, still their recent information, it gets higher weight. Data that we dealt with was all tabular data. We were dealing with demographics, CPT, ICD code, lab results, as well as the medications. We decided to use simple fusion techniques, for example, late fusion, where you train a separate classifier, separate model for each of the modalities, and then combine their probability estimates, and then pass them through a meta-learner before you get a final prediction. It obviously has its limitations, like different modalities, they're not learning from each other, they're being trained separately. Another was this early fusion, where you basically concatenate all of the features and train one model. This is all tabular clinical data. So this kind of fusion modeling might work, but essentially you can see that this has its limitations. I mean, you cannot really hope to combine like an imaging modality with all of these clinical data, because it's just concatenating features that might mean very different things into like one big vector. And other one is this middle fusion, which is more like a branch neural network. So you have these 5 branches dealing with 5 of these modalities. They map these modalities to some representative vectors, and those vectors are combined, concatenated, and then passed through a final classification layer. It's different from late fusion because everything is trained at the same time for minimization of the same loss. So still modalities get a chance to learn from each other. Still, it can be hard to figure out like a good structure for all of these branches. For this kind of model, we still saw that simple fusion techniques, early, late, and middle fusion, they tend to outperform all of our single modality models. But this project was limited in the sense that we were only looking at the tabular data. We were not looking at imaging data. With the next part of the project involved looking at imaging data and combining it or fusing it with the clinical data. Once you have like these two very different different data modalities, we decided to use this graph structure, which gives you like these two sub data structures within one. You have nodes and you have edges. So if you have like two different data modalities, you can fill, let's say, nodes with one of them, and you can base your edge decisions on the other one. So that's what we decided to do. We decided edges based on clinical similarity of patients, and we decided to use X-rays as node features. Project was about inpatient COVID-19 population. The patient has already been admitted to the hospital with a positive diagnosis of COVID-19. And we want to see how the patient would progress throughout the hospitalization. So every time there is a new chest X-ray taken by the patient, taken for the patient, we make a new prediction, whether the patient will be discharged from the hospital or patient will need ICU admission, or there's a risk of mortality. Again, as I mentioned earlier, we used this relational graph modeling, and we also did external validation for this project. This work is under review in the CAI 2022. So as I described earlier, relational graph, edges versus nodes. So we decided to use clinical data like CPT and ICD codes and demographics to decide edges between nodes. And nodes are simply DenseNet one-to-one features for chest X-rays. Graph neural network would allow this kind of twofold learning, where the network is, of course, learning from the node features or the X-ray features of the node itself, but it also getting messages from node features or chest X-rays of clinically similar patients because they are connected through edges. They are edge-connected nodes, or they form the neighborhood of a node. So with this kind of twofold learning, it can predict better prediction. It can make more accurate predictions for the node itself. External validation showed us a very nice property of these relational graph-based models. Traditionally, you would have to use exact same set of features going from your internal data to your external data, because your input samples, they need to be in the same space for application of a pre-trained model. This is true for node features in this case. So we use the same DenseNet one-to-one to create node features or chest X-ray features in our external set as well. But edge decision, all the graph neural network needs is a built graph. It doesn't put any limits on how that graph was created. For example, in our internal set, we had this graph built by common CPT subgroups between patients. And here is a list of common CPT subgroups ordered ordered by their frequency. And here is the common CPT subgroups of our external set. Since both of these sets, they are COVID-19 cohorts. So you see similar CPTs like heart disease or hypertensive disease or respiratory system disease. But you also see very distinct CPTs, for example, nephritis or neoplasms. They were part of our internal set. They were very common in our internal set. On the other hand, external set, we had this distinct CPT subgroup of diseases of the nervous system. So we don't have to ignore this difference. So we used common CPTs of the internal set to create edges for the internal set. And we use common CPTs of the external set to create edges for the external set. And once we had these this graph built, we could still use the same pre-trained GNN that we have trained over our internal set. With this kind of property, we saw that for all three of our prediction tasks, discharge, mortality, and ICU admission prediction, on both our internal and external sets, our graph-based models, they performed much better than our single modality models like NH only and EHR only models. We also did bias analysis on our project. So bias or disparity, we used Equitest toolkit that measures bias or disparity in terms of either false positive rate or false emission rate. For example, if your for example, ICU admission, it's an assistive measure for the patient. So being falsely omitted from that group that gets admitted to the ICU, that's a bias against you. Discharge from the hospital, if you are being falsely predicted positive for the discharge from the hospital, that's a bias against you. There have been lots of studies to show that these clinical decisions, these factors, they are affected by socioeconomic factors or insurance status or race. So with the help of our clinical experts, we identified these three factors which were available in our data, reported history of alcohol abuse, race, as well as insurance. And we looked at the disparity in different groups based on these factors. And we realized that, yes, the bias is there. For example, our discharge prediction model, it seems to be biased against the people with reported history of alcohol abuse. Medicaid insurance seems to be a negative factor when it comes to ICU admission. So in this project, this is more of a limitations study. We know that we have built this predictive model. We want to see what's the limitation of this model. So this model is learning from the labeled data available. That labeled data is actually coming from the COVID-19 cohort and how it moved through the hospital, how it was admitted, when it was discharged, when someone was admitted to ICU. So our model is also picking up on kind of known biases of these clinical decisions. So in this project, we are not doing anything to mitigate this bias. This is more of a limitation study, but that opens up a lot of space for us to think about making sure that this bias is mitigated. You have a way of debiasing your model. Moving on, we have, I've presented projects where we have combined this different types of clinical data and then clinical data with the imaging data. The thing that is still missing is that, medical data is temporal. So the patient doesn't get just like one imaging study, there may be a series of imaging studies. Similarly, your clinical data, your ICD, CPT labs and medications, they're also temporal. So how do we deal with that temporality? For that, for the next project, I'll introduce our work on basically multimodal spatiotemporal GNN, graph neural network. So where you assume that there is just not like one snapshot of the graph, you have a new snapshot of your graph at each time point. And that snapshot is updated in terms of node features. You get new node features for that snapshot. Application for this particular project was this prediction of 30 days readmission for all of the inpatient population. So we moved beyond COVID-19 cohort and we decided to look at all of the inpatient population. And as you know, 30 days readmission is a quality measure for US healthcare system. We want to avoid that preventable readmission to the hospital. So preventable, in this case, challenge is again that we have this temporal inpatient data. So we look at all of the data. Patient gets admitted to the hospital and then patient is discharged. And then when the patient is being discharged, we want to predict whether the patient will be coming back in 30 days. So we get all of this inpatient data, but that's temporal. If you stay in the hospital for 7 days, there may be like multiple imaging studies. Of course, you'll get multiple CPT, ICT codes and labs recorded. So again, in this case, we used chest X-rays as our imaging features, but as you can see in this figure, that you have your chest X-rays, which is basically a time series, and you have these the clinical data as well. So we again use clinical data to build a graph of clinically similar patients. But now this graph has multiple snapshots. Every time there's there's a new chest X-ray, that's a new snapshot of your graph. And to treat this graph, we use this spatiotemporal graph neural network, which is also multimodal. So in this case, we have these two branches of the network. One branch looks at the imaging features or the chest X-rays as node features, and the other one looks at clinical features as the node features. And both of these branches, they generate node features, which are concatenated, passed through an MLP to make the final prediction. And I'll show how this kind of multimodality helps us deal with the larger variety of inpatient population. These are the results. We experimented with two data sets. One was collected from the Mayo Clinic itself, and the other one was this MIMIC4 data set. And you can see that multimodal spatiotemporal GNN that outperforms several baselines. With temporal model without the relational graph model, relational graph without the temporality, EHR-based models only, imaging-based models only. So the best performing combination is when you fuse information from EHR and imaging, when you're using this multimodal spatiotemporal GNN. Here is the interesting result. Since it's like all of inpatient population, so we process their clinical notes, and we extracted the primary diagnosis for each patient. And we mapped that we used NLP to first extract these and then map these primary diagnoses to human disease ontology. And we realized that like these are the three most common disease subgroups in our cohort: heart disease, vascular disease, and then metabolic disease. Maybe this should explain like why we need this kind of multimodality, because maybe heart disease and vascular disease patients, you get a lot of information from their imaging studies. But metabolic disease patients, maybe you have more information coming from their electronic health records. So the branch that deals with electronic health records or clinical features as nodes, it may be more highly weighted for this cohort or subcohort as well. So multimodality helps us deal with a larger variation in our inpatient population. Again, these models are completely replicable. Their downstream prediction task isn't really fixed. It depends on what's useful in any scenario. Like we've gone from predicting hospital admission to hospital discharge to 30 days readmission. So these are all replicable pipelines. Explainability is another scenario. In this kind of relational graph modeling, gradient-based approach may not be enough to explain the output. Updation studies I've shown you, we know that, okay, we have done models without relational graph, we've done models without temporality, without imaging, or without EHR. And so we know that each component has a role to play. So in this case, we want to see how the neighborhood is affecting any output. So there are these mutual information maximization, which looks at different sub-networks and puts a weight on that network based on how important that sub-network is for the final prediction. For example, this is from that COVID-19 cohort, and both of these nodes, they are true positives for adverse outcomes. So this node, it's expiration in 3 days or mortality in 3 days. And this one is like longer hospitalization. Patient is not discharged in the next 3 days. First, you can see, and these edge weights, they are not the original edge weights. This is the edge weights assigned by the model itself. That's how much model thinks it's important for the prediction of this node. As you can see, first, for the case of discharge, adverse outcome node, it's higher. Its neighborhood can consist of many other nodes with adverse outcome. That's one thing. The other thing is that since this network was originally built on common CPT subgroups, so here's a list of common CPT subgroups from both of these neighborhoods. As you can see, procedures like high-risk procedures like surgical procedures on cardiovascular system, they are both present. They are present in both of these neighborhoods. So we can see that for an adverse outcome or a high-risk patient, the model learns to put higher emphasis on the neighborhood nodes consisting of other high-risk or adverse outcome patients. Here's another example. This is from the 30 days readmission project. Here you can see this one is an adverse outcome. Patient was readmitted to the hospital in 30 days. And model thinks that this neighborhood node, this edge connected node, is the most important. And you can see the primary diagnosis for both the central node and this neighborhood node. It's the same: vascular disease or heart disease. So even though we're not using this primary diagnosis directly into the model still learns to associate patients with similar kind of clinical background. Overall, in my overall vision of the research, it fits into the fusion modeling because I'm trying to combine different data modalities. And it's also like one target application that we have seen is clinical event prediction. For future research, of course, I want to work towards that goal of digital phenotyping of patients. I'm interested in temporal evaluation or temporal evolution of this kind of phenotyping at both long-term and short-term level. For example, short-term might be inpatient population, how this evolution, this phenotyping evolves through your stay in the hospital, or how it evolves on a longer time scale maybe. particular applications or application areas that I'm interested in, in cardiovascular disease and mortality and graft failure prediction for kidney transplant patients. This kind of research, it needs a lot of collaborative effort. So I have worked with experts from all of these different institutes in past, and I plan on keep on building this kind of collaborative environment. Again, since I'm coming from a background in computer science and working in this area, I want to target both, clinical funding resources like NIH and NSF. In University of Colorado, I can see a lot of potentially interesting collaborations. With Hunt Lab, they're working on this information extraction from biomedical literature, which again fits into this vision of pseudo annotation for my imaging data. TIS Lab, they're working on these ontologies. I'm interested in using those ontologies to build these, the clinically similar networks of clinically similar patients, which can be further leveraged while you're making predictions for one patient. Similarly, since I'm interested, I'm always working with some sort of radiologic images, so School of Medicine, Department of Radiology, as well as UC Health Transplant Center. These are the two departments that I want to connect with. I have 3 years of teaching experience, and I've taught artificial intelligence and machine learning courses. I've taught students. I'm currently mentoring an ASU capstone project. There are some of the papers that I've written with some of my mentees. This is all for my presentation. Please let me know if you have any questions. Thank you very much for listening.
So I guess, I'd love to get, a bit of a sense from you if there were kind of any themes over the projects that you did that sort of had, was there sort of a take home of, if you're approaching this kind of problem, approach it in this way, that sort of spanned more than one project?
Okay, so I divided it into streams because most of the take homes from one stream that was applicable on all of the projects of that stream. For example, in all of my language modeling projects, the whole idea was that you have lots and lots of domain variation. And you need to use kind of simplistic techniques. You don't need something really complex, but by using just transfer learning or by using just this text standardization, you can improve the performance of your model. And it fits into, again, if I'm doing this, the other part of the other stream that I showed you, it was all about clinical event prediction using this fusion modeling. And the fusion model, you could see we have imaging data and we have clinical data. But again, larger scheme of things, and in other projects that I want to work on, I want to include clinical notes as well. So the language modeling part of the other stream that I presented, it's going to become important in 2 ways. First, I'm hoping that it'll give me more annotation for my imaging data, part 1. And secondly, I'm hoping that it's going to give me better representations for clinical notes, which of course is going to be temporally evolving. So both of these are connected and then distinct in some manner as well. Thank you.
Yeah, thank you, Dr. Tariq. I really enjoyed your talk, and it's an impressive array of work. I just want to sort of explore practicality in some of the models, in that text and imaging have the potential to contain quite a bit of knowledge that hasn't been easy to integrate into clinical decision support. There's always the question of, are the more complex model types and the more complex data inputs worth it? Do they really provide clinical benefit that is sufficient for the extra effort? And to that point, for example, you showed the slide where the LSTMs, just a recurrent neural network over the EHR data, performed very nearly as well as the models integrating imaging data. And so I wonder, how do you think about those questions, and how do you build in kind of pragmatism into your studies?
Oh, that's an interesting question. So one thing is basically piece by piece evaluation, so that you know that everything you're doing, it has some value to add. That's why, when I mentioned my potential collaborations, I'm very interested in this, in people who are doing this ontology-based work. Because like in my work, you might have gotten the impression that I want to take just raw text and raw images and then put them together and build some comprehensive model. But is it really worth it building that complex model? Or you want to do it piece by piece? I'm going to say, okay, we have this textual data. We have this huge field of ontologies and everything. Can we use that raw data to facilitate that ontology construction? And once you have that ontology construction already done, use this to build your network. For example, we have these ICD CPT codes and their structure available. So use that to build connections instead of, just plugging in raw clinical notes and hoping that it would give you good clinically similar patients connected to each other. One in that like piece by piece evaluation. That's why I consider, these collaborations important, so that you know that you're not just building an overly complex model for nothing. You have like a piece by piece, way of seeing that this works. Okay, this is important. Then maybe this output can feed into the next step of the project. I think that's one. And other part is that some of the things that you think like, okay, this seems to be working just as well with the LSTM and EHR along with the imaging model. We saw more of this in our readmission project, where we were dealing with a larger variety of patients. So if you're talking about generalization, then maybe you're able to deal with a particular subset of your cohort, because you have that, which looks like a rather complicated model. For example, we're doing this multimodal STGNN, and then we know that this, if we look at it, on parts of the population, we can see that this is good for vascular disease patient, this is good for heart disease patient, but potentially for metabolic disease patient, maybe it would have been good to just use one branch of the network. But that's kind of the, kind of drawback of trying to make it more generalizable. Maybe there's part of your complex network that isn't really necessary for a small portion of for your cohort, but it's still there because it makes it generalizable to the rest of the population, and you don't have to go build two different separate models, which would have their own complications, of course. I hope that somewhat answers your question.
Lots to talk about. Thank you.
Thank you.
I have a question.
Sure.
Did I hear you right that each time you got a new data, like each time you scanned a new, let's say you got a new X-ray, did you add a node into the graph?
Yes. I've talked about two projects. In one case, this was the COVID-19 cohort, where we were trying to predict hospital discharge, ICU admission, or mortality. In that case, every time there is a new chest X-ray, we added a node to our network. And the other one was just 30 days.
Does the one where you add a node for every image, is it the same network for all patients? So are all X-rays captured by the hospital a node in the graph?
Yes, essentially, yes. Yeah.
Okay. And then how did you choose how you were going to relate, like which nodes were connected to which nodes?
Yes, so one thing is our edge structure is based on clinical information, the ICD, CPT codes, and demographic information that we are getting. Mostly demographic information is not changing, but ICD, CPT codes, as you stay in the hospital, you get like more codes, different codes. So we made sure that every time we have a node to connect, we look at the time point of the chest X-ray. And we only use the ICD and CPT codes recorded before that time point to see the similarity between different nodes. So for even if the chest X-ray is like same patient gets 3 different chest X-rays, it doesn't, all 3 of those nodes, they don't get the same set of edges, because their corresponding clinical features, their ICD, CPT codes, they may be evolving.
Are those codes, do those codes include diagnoses?
Yes, ICD codes, they're supposed to include diagnosis.
Okay, thank you.
Thank you very much.
Okay, well, we're above the top of the hour, but thank you so
Mhm.
much for taking the time to chat. And I look forward to our meetings later and then a chance to hear more about your vision tomorrow. Thank you.
Thank you very much. Thank you.